The dawn of the cislunar economy is no longer the province of science fiction writers or far-future visionaries. It is a tangible, unfolding reality, driven by a convergence of technological maturity, geopolitical competition, and a fundamental shift in how humanity approaches spaceflight. We are moving from an era of flags and footprints, defined by discrete, destination-focused missions, to an era of supply chains and sustainability. This transition is creating a new industrial geography between the Earth and the Moon, a region known as cislunar space. This analysis explores the emerging cislunar logistics network that will serve as the foundation for the Moon-to-Mars economy, delving into the infrastructure being built today, the economic models driving it, the critical technologies required, and the complex geopolitical landscape that will govern this new frontier. To understand the logistics of the future, one must first understand the terrain. In space, terrain is defined not by mountains and rivers, but by gravity wells, orbital mechanics, and energy budgets, specifically delta phi. Cislunar space is the volume of space influenced by the gravity of the Earth and the Moon. It is vast, extending roughly 1.5 million kilometers from Earth. However, it is not a uniform void. It is structured by invisible pathways and strategic high grounds. Just as maritime trade relies on shipping lanes and currents, cislunar logistics relies on specific trajectories that minimize fuel consumption. The most critical of these are the Lagrange points, 5 locations in space, where the gravitational forces of the Earth and Moon balance the centrifugal force felt by a smaller object. First, there is EML1, the Earth-Moon Lagrange Point 1. Located between the Earth and the Moon, about 85% of the way to the lunar surface, EML1 is the ideal location for a toll booth or a primary logistics hub. It offers a vantage point that commands the near side of the Moon and serves as a staging ground for descent to the surface. Then there is EML2, situated behind the Moon from Earth's perspective. This is the gateway to the outer solar system, and a perfect location for a propellant depot supporting Mars missions. It allows for halo orbits that provide continuous communication with the lunar far side. Additionally, we have the Near Rectilinear Halo Orbit, or NRHO. This is the chosen orbit for NASA's Lunar Gateway. It is a highly stable elliptical orbit that passes close to the lunar north and south poles, offering easy access to the surface for landers while minimizing the fuel needed to maintain the station's position. The fundamental economic driver of cislunar logistics is the rocket equation. Launching mass from Earth's deep gravity well is energetically expensive. It takes roughly 9.3 kilometers per second of delta phi just to reach low Earth orbit. In contrast, launching from the Moon's shallow gravity well requires only about 2.3 kilometers per second to reach a similar staging point. This disparity creates the central business case for the Moon-to-Mars economy, which is resource extraction. If fuel, specifically hydrogen and oxygen, along with water and building materials, can be sourced from the Moon or asteroids, they do not need to be lifted from Earth. This shatters the tyranny of the rocket equation. Early analysis suggests that sourcing propellant from the Moon for a Mars mission could reduce the mass required to be launched from Earth by over 40%, fundamentally changing the economic viability of interplanetary colonization. A supply chain is only as good as its vehicles and nodes. The cislunar economy is rapidly moving away from expendable rockets toward a complex ecosystem of reusable transport vessels and permanent orbital infrastructure. In the old paradigm, a rocket upper stage would push a payload to its destination and then become space junk. In the new paradigm, we are seeing the emergence of orbital transfer vehicles, or space tugs. These are reusable spacecraft designed to ferry cargo between orbits. Consider Impulse Space's Helios, a high-energy kick stage designed to take payloads from low Earth orbit to geostationary orbit or the Moon in under 24 hours. Unlike electric tugs, which are slow, Helios uses liquid methane and oxygen to provide the high thrust needed for rapid transit, crucial for time-sensitive biological cargo or crew supplies. Then there is the momentous Vigoride. Using innovative water plasma propulsion, Vigoride represents a class of last-mile delivery vehicles. While smaller than Helios, its use of water as propellant aligns perfectly with a future where lunar ice is mined and processed into fuel, making it a potentially self-sustaining piece of the ecosystem. For heavy logistics, such as moving 50-ton habitats or massive fuel tankers, chemical rockets are too inefficient. Companies like Atomos Space and government programs like DARPA's Draco are developing nuclear thermal propulsion. NTP uses a nuclear reactor to superheat a propellant like hydrogen, expelling it at high speeds. This technology doubles the efficiency of the best chemical rockets, effectively shrinking the solar system and allowing for rapid, heavy-lift transport between Earth, the Moon, and Mars. The tyranny of the rocket equation implies that long-duration missions are limited by the fuel they can carry. Orbital propellant depots solve this by decoupling launch from transit. We are looking at massive storage tanks in low Earth orbit, where starships or other heavy lifters can top off before heading to the Moon. This allows a vehicle to launch with maximum cargo and minimum fuel, refuel in orbit, and then depart with a full tank. Furthermore, Cislunar depots, located at EML-1 or NRHO, would store lunar-derived propellant. A Mars-bound ship could leave Earth empty, saving massive launch costs, fly to EML-1, fill up with lunar oxygen and hydrogen, and then burn for Mars. An emerging concept involves recycling space debris via metal propellant nodes. Using metal-fueled thrusters, scrapyard depots could grind down old satellite casings and turn them into fuel pellets for tugs. This creates a circular economy in orbit, cleaning up debris while powering logistics. NASA's Lunar Gateway is the first permanent piece of cislunar real estate. Orbiting in NRHO, it is not just a habitat, but a multimodal logistics hub. It will host visiting vehicles, aggregate cargo, and serve as a command post for surface operations. However, commercial players are planning their own business parks. As the ISS retires around 2030, private stations from Blue Origin, Voyager Space, and Axiom Space will take over. These will likely serve as the Earth-side manufacturing and consolidation hubs for goods heading outward. On the surface, operations at the lunar South Pole, such as at Shackleton Crater or Malapert Massif, will require landing pads, charging stations, and cryo-storage. These moonports will be the interface between the vacuum of space and the resource-rich regolith. The engine of the cislunar economy is In-Situ Resource Utilization, or ISRU. Without the ability to live off the land, the moon remains just a tourist destination. With ISRU, it becomes an industrial powerhouse. Data from the Lunar Reconnaissance Orbiter and Chandrayaan-3 confirms billions of tons of water ice trapped in the permanently shadowed regions of the lunar poles. Mining rovers like NASA's Viper or commercial successors will venture into these dark, negative 230 degrees Celsius craters. They will drill into the rock-hard regolith, sublimate the ice, capture the vapor, and transport it to a processing plant. Water is life. It is drinking water for crew and radiation shielding for habitats. More importantly, when split via electrolysis, it becomes hydrogen for fuel and oxygen for breathing air and oxidizer. PwC estimates the cumulative lunar market could reach $170 billion by 2040, with resource utilization being a primary driver. Selling propellant in lunar orbit at $500,000 per ton is vastly cheaper than shipping it from Earth at over $1 million per ton, creating an instant market for early mining operations. Beyond water, the lunar soil or regolith itself is a resource. Regolith is roughly 40 to 45% oxygen by weight, found in silicates and metal oxides. Processes like molten regolith electrolysis can extract this oxygen, leaving behind metal alloys like iron, aluminum, and silicon. Companies like Icon are developing technologies to sinter regolith into landing pads, blast shields, and habitats. Launching concrete from Earth is impossible. Printing it on the moon is essential. This dust-to-structure capability will lower the cost of expanding lunar bases effectively to near zero for raw materials. Industrial mining requires megawatts of power, far more than solar panels can provide during the 14-day lunar night or in shadowed craters. NASA and private partners are developing small, modular fission surface power nuclear reactors. These reactors are robust, independent of sunlight, and dense enough to be launched on standard rockets. To get power into the dark craters where the ice is, Tower of Power Concepts propose tall solar masts on crater rims, beaming energy via laser or microwave down to rovers in the dark below. The Moon to Mars architecture is not just a slogan, it is an engineering dependency. The moon is the proving ground and the gas station for the Red Planet. A human mission to Mars requires a massive amount of mass, roughly 300 to 500 metric tons departing Earth orbit. Launching this on a single rocket is impossible. Instead, the mission is aggregated in cislunar space. The habitat is launched to NRHO, or high Earth orbit. The propulsion bus is launched separately and docked. Then comes the fuel. This is the game changer. Instead of launching fully fueled tankers from Earth, the Mars ship is fueled by lunar-derived oxygen and hydrogen delivered by cislunar tugs. This reduces the number of Super Heavy class launches from Earth required for a Mars mission from roughly 10 or 12 down to just 4 or 6. It turns the moon into an anchor tenant for the Mars logistics system. Furthermore, Mars is 6 to 9 months away, while the moon is only 3 days away. If a CO2 scrubber fails on the way to Mars, the crew dies. If it fails at the Lunar Gateway, the crew can abort home. The cislunar shakedown cruises will push closed-loop life support systems to their breaking points in a safe fail environment. Surface operations also benefit from this proving ground. Dust on Mars is toxic and abrasive. Lunar dust is razor-sharp and electrostatically charged. Mastering dust mitigation on the moon is a prerequisite for Mars survival. Who pays for all of this? The transition from government funding to commercial revenue is the valley of death for cislunar logistics. However, the business case is strengthening. Analysts project the global space economy to reach $1.8 trillion by 2035. While much of this is satellites and Earth observation, the cislunar slice is growing. NASA's Artemis program and the China-led ILRS are the initial anchor tenants. They are signing contracts worth billions for delivery services, landers, and spacesuits. This government spending de-risks the technology for private players. Commercial revenue streams are emerging, including propellant sales to NASA and ESA, disposal of dangerous orbital debris into graveyard orbits via cislunar tugs, and the data and PNT market. A constellation of satellites around the Moon, providing navigation and high-speed internet, known as LunaNet, is a service that every lander and rover will pay to subscribe to. We also see a sovereign commercial nexus, where nations without their own launch capabilities are paying US and Japanese firms to fly their payloads to the Moon. The heavy lifting is done by giants like SpaceX and Blue Origin, but the ecosystem is filled with agile specialists. Firefly Aerospace offers specialized tug services and lunar landing capabilities. Astrobotic and intuitive machines act as the FedEx of the Moon, handling the complex logistics of landing payloads. Cislunar Industries focuses on in-space metal processing to turn debris into rods for electric thrusters. This diversity creates a resilient supply chain, preventing the single point of failure risks that plagued the shuttle era. Space Law is the software that allows this hardware to operate, and currently, it is a buggy beta version. The 1967 Outer Space Treaty is the constitution of space, but it is vague on resource extraction. The Artemis Accords, led by the US, interpret the OST to allow for the extraction and ownership of space resources. Signatories agree to safety zones around their operations to prevent interference, creating a club of nations operating under Western norms. Competing with this is the International Lunar Research Station, or ILRS, led by China and Russia. While the scientific goals are similar, the governance model is different. This bifurcation creates a risk of balkanization in cislunar space, with separate supply chains and potential friction over prime real estate at the lunar South Pole. With thousands of satellites projected to enter cislunar space, space traffic management is critical. Currently, there is no central air traffic controller for the Moon. If a Starship and a Chinese Long March 10 are on colliding trajectories, who moves? Concepts like the Cislunar Traffic Management System are being developed to coordinate orbits and radio frequencies, aiming to establish rules of the road before a collision occurs. If these trends hold, what does cislunar space look like in 2040? Imagine a cargo shipment leaving Earth. It launches on a reusable super heavy lifter to a low Earth orbit depot. There, the cargo container is transferred by robotic arm to a nuclear thermal cycler tug. This tug never lands. It shuttles endlessly between LEO and the EML-1 gateway. The journey takes days, not months. At EML-1, the cargo is offloaded. The tug refuels with liquid hydrogen shipped up from the Shackleton Industrial Zone on the lunar surface. The cargo container is then loaded onto a lunar descent shuttle for the final leg down to the surface, or perhaps transferred to a Mars transfer vehicle assembling at EML-2. On the lunar surface, Artemis Base Camp is a bustle of activity, with mining engineers, reactor technicians, and hydroponic farmers. The lights never go out, powered by fission reactors. In the distance, a masked driver shoots canisters of processed oxygen into orbit to catch the next tug. This is the Cislunar Logistics Network. It is the infrastructure that turns space from a place we visit into a place we live. It is the bridge that transforms humanity from a single planet species into a multi-planetary civilization. The Moon to Mars economy is not just about going there, it is about building the supply chain that ensures we can stay there. To fully appreciate the scale of this endeavor, we must look closer at the specific technologies. Storing liquid hydrogen and oxygen in space is a nightmare due to boil-off. Future depots will use zero boil-off technology with active cryocoolers to keep fuel liquid indefinitely. Transferring liquid fuel in zero gravity is also difficult. New technologies using surface tension vanes and settling thrusters are being tested to ensure that when you pump fuel you get liquid, not gas. Autonomous rendezvous and docking will become routine. Tugs will use advanced LiDAR and computer vision to build real-time 3D models of their targets, allowing for autonomous docking even in harsh lighting. Standardized interfaces like the International Docking System Standard ensure interoperability between different providers. In-space manufacturing allows for spare parts on demand. A Mars mission cannot carry a spare for every bolt, so they will carry 3D printers and feedstock to print replacements. This also allows for recycling waste plastic into printer filament. While robots will do the heavy lifting, the human element remains essential. We are moving beyond the scientist-astronaut to the orbital blue-collar worker. The future demands technicians, electricians, and mechanics. Working in cislunar space involves exposure to radiation, so medical logistics will be a major service industry. Training centers on Earth will simulate industrial operations like repairing jammed drills or managing propellant transfers. Living at the Lunar Gateway or a commercial station in NRHO brings isolation and long supply lines. Return from NRHO takes days, so logistics planning for food, medicine, and morale becomes a critical safety discipline. Building the Moon to Mars economy is the greatest logistics challenge in human history. It requires coordinating assets across hundreds of thousands of kilometers, managing supply chains with zero margin for error, and inventing entire industries from scratch. It is a challenge that involves aerospace engineers, economists, lawyers, geologists, and diplomats. The rockets are being built, the contracts are signed, the maps are drawn. The first shipments of the Cislunar era are already on the manifest. We are witnessing the construction of the road to the stars, and it is paved with logistics.